origin of the aurora begins on the surface of the sun. Solar activity ejects a cloud of gas, also known as a coronal mass ejection. It takes about 2 to 3 days to reach Earth. When it reaches Earth, it collides with Earth's magnetic field. The Earth's magnetic field is an invisible field that, if visible, would look like a comet with a magnetic tail on the opposite side of the sun. When a coronal mass ejection collides with the magnetic field, it causes complex changes to happen to the magnetic tail region. These changes generate currents of charged particles, which then flow along lines of magnetic force into the polar regions. These particles are boosted in energy in Earth's upper atmosphere, and when they collide with oxygen and nitrogen atoms, they produce dazzling auroral lights. They are visible any time during the year. In some areas such as Alaska or Greenland, they may be visible most nights of the year, and they can occur at any time of the day, but we can't see them with the naked eye unless it is dark.
When the charged electrons and ions collide with oxygen 60 miles above the surface, it causes a typical yellowish-green light in the sky. When they collide with oxygen 200 miles and above, this causes a reddish-orange aurora in the sky. When nitrogen is blasted by these charged particles, it produces a blue light, and neutral nitrogen produces a red or purple light. On the sun's surface, where the temperatures are millions of degrees Celsius, collisions of the gas molecules make the gases very agitated and causes huge explosions. Hotspots on the sun's surface are the origin of these explosions. These charged particles are positive ions, and electrons are blown off the sun's surface. They are blown at such a rate of speed, they escape the sun's powerful gravitational pull and are expelled into the universe. These events, that happen on the surface of the sun, are called solar flares. These charged electrons and protons race towards the Earth at speeds of nearly 1 million miles per hour. Once the charged particles reach the Earth, they are traveling at speeds of 400 kilometers per second. The Earth has a magnetic field that deflects most of these charged particles from reaching the Earth's atmosphere. It flows around the magnetosphere like a river flows past a rock, but some of these particles will reach the Earth's atmosphere where the magnetic field is the weakest. This typically happens at the poles. When the charged particles reach Earth's magnetosphere, they collide with the gases that are within Earth's upper atmosphere. This puts the atoms of the gases into an excited state. The atoms then settle back down to their normal state and release energy. This is shown in the form of light that we observe as the aurora. Auroras normally occur near the poles, but if a solar storm is powerful enough to break through the magnetosphere, the aurora can be observed further towards the equator. Typically, a person will be able to see an aurora once in a lifetime if they live in Mexico, Southern Europe, or the Southern United States.
The beautiful colors of the Aurora Borealis seen in the night sky are formed hundreds of kilometers above the ground. Generally, the top of the aurora reaches its peak around 300 kilometers, but can reach even as high as 600 kilometers. Its lowest elevation occurs at around 80 kilometers. The interval of where the Aurora Borealis takes place is where the ionosphere lies. It is not its own layer of atmosphere, but rather an augmentation of the thermosphere. With an altitude that can reach up to 600 kilometers, the ionosphere is the closest part of Earth's atmosphere to the Sun. This allows the molecules of the magnetosphere to be ionized, or broken apart, by the ultraviolet radiation of the Sun. The solar wind from the Sun then connects with the magnetosphere of the Earth and pulls it towards the northern latitudes of the Earth. As majestic as they are in the night sky, the effects of the Aurora Borealis are the source of numerous predicaments on the ground level. For example, they can cause blackouts due to their strong electrical charges if they come into contact with power lines. Furthermore, the ionosphere influences the interaction of radio waves, and aurora can dislocate short-wave transmissions. These negative effects of the Aurora Borealis are contradictory with its grand appearance.